In this video, we will talk about the molar enthalpy of formation. Before we start, we have to look at our symbolism once again. The delta H, of course, refers to the enthalpy change. The F here symbolizes a formation reaction. And if you recall from Science 10, a formation reaction is when individual elements create a compound. We had A plus B forming the compound AB. An example here is hydrogen reacting with oxygen to produce water. The next symbol we want to look at is the little degree sign, and we mentioned that this is the symbol for standard conditions, 1 atmosphere and 0 degrees Celsius. So the standard enthalpy of formation is basically just the enthalpy change from the measurement of a formation reaction done under standard conditions. Because standard molar enthalpy of formation is very useful in chemistry, chemists have created a table, a data table, and this table is in page 4 and 5 of a Chemistry 30 data booklet. Let's look at some example values. We see that the formation of carbon dioxide and water is an exothermic process, whereas the formation of nitrogen monoxide and ethane is an endothermic process. Therefore, there is no real trend that we can see if a process will be exothermic or endothermic. And once again, this is a molar heat of formation. That means it is for 1 mole of the product. Note that sometimes you may need to use fractional coefficients to ensure that the coefficient for the product, the compound, is 1. Let's revisit 2 of the ways that we can express an enthalpy change in a chemical equation. One of the ways to do it is to include the energy term within the equation. Here, in the formation of carbon dioxide, we include the energy term as part of the product. Because it's part of the product, we know that it's going to be an exothermic reaction. An alternate way to express this is using the enthalpy change, or to state the enthalpy change distinctly from the equation. Because in an exothermic reaction, the delta H value will be negative. On the other hand, if we look at a different reaction, an endothermic reaction, we see that in the formation of benzene, the energy term is part of the reactant. Therefore, we know this is going to be an endothermic reaction. So when we state the delta H value outside of the chemical equation by itself, this will be a positive enthalpy change. Let's look at a couple more hints from the standard enthalpy of formation table. In our table, those are formation reactions. The data given is for formation reaction. And these are also known as simple composition reactions. And this is again when you have 2 elements making a compound. However, the reverse of that is a decomposition reaction, when you have a compound breaking down into its elements. According to the second Hess's law rule, when a reaction is reversed, then we have to take a negative of the enthalpy change. Here you see that for the simple decomposition of carbon dioxide, the enthalpy change is positive 393.5 kilojoules, whereas for the simple formation reaction, as stated in our data table, it's negative 395.5 kilojoules. As well, because elements are not compounds, their enthalpy change is 0. Therefore, you will not find any enthalpy change for any elements. This is for things like nitrogen gas, oxygen gas, carbon, fluorine gas, or any of the halogens. Let's look at an example. We're asked to find the formation equation for aluminum oxide. So if you were to write a normal formation reaction, you would have aluminum reacting with oxygen to produce aluminum oxide. If you were to balance this equation, you would say, oh yeah, I would need 2 of that to give us 3 pairs of oxygen and 4 aluminums. However, in this balance equation, the mole of the product is 2. However, when we do standard formation reactions, we have to have a coefficient of 1 for the compound that we're interested in. To do that, we need to divide all the coefficients by 2. So 4 divided by 2 becomes 2, 3 divided by 2 is 3 halves, and 2 divided by 2 is 1. So therefore, in our final equation, we have 2 aluminums plus 3 half oxygens yields aluminum oxide. If we are to write the energy term as part of the equation, we would put it into the products because the table value is negative. Negative implies an exothermic reaction, so we have to put the energy term into the products. We could also write it outside the equation as a simple delta enthalpy change, and this would have a negative value because in an exothermic reaction. When we do a potential energy diagram for formation reaction, we can actually put values into our y-axis because we know that all the elements have a potential energy of 0. So all our reactants should have an energy value of 0, and for exothermic reactions, the products will have a negative potential energy value. Here in this case, it will be approximately negative 1,635 kilojoules. Sorry, 1,675 kilojoules. Let's look at another example. Here we want to find the equation for the formation of nitrogen dioxide. Normally you would write nitrogen plus oxygen yields nitrogen dioxide. To balance this equation, you need a coefficient of 2 in front of the nitrogen dioxide and 2 in front of the oxygen. However, we need to have a coefficient of 1 in front of the nitrogen dioxide, so we need to divide everything by 2. Divide everything by 2, so that our final equation becomes half a nitrogen plus 1 oxygen yields nitrogen dioxide. And according to the table of formation, standard enthalpy of formation, this is an endothermic reaction and is 33.2 kilojoules. If we were to include the energy term in the equation, we would put it on the reactant side because it's an endothermic reaction. And if we express the enthalpy term outside the equation, it would be positive because it is an endothermic reaction. Again, if we were to put this onto a potential energy diagram, we would put our reactants, the elements, at 0, and then our products, nitrogen dioxide, would have a positive value of 33.2 kilojoules. Let's take a moment to talk about the stability of compounds. When compounds are formed from the elements, sometimes they release energy. And the more energy they release, the more stable the product compounds will be. So if we look at the formation of various sulfur oxide compounds, we see that the formation of sulfuric acid releases the most energy. That means this sulfuric acid will be the most stable of the sulfur oxide compounds. Conversely, the sulfur dioxide compound releases the least energy. That means this is the least stable of the sulfur oxide compounds in this table. We could also take the data from our previous slide and put them onto a potential energy diagram. Here you can see that, again, sulfur dioxide releases the least amount of energy. It is the least negative, whereas sulfuric acid is the most stable. It is the most negative. And we can see that, again, the sulfuric acid is the most stable, whereas the least stable is the sulfur dioxide. Lastly, let's talk about what these table values are good for. We can use these table values to predict the enthalpy change for single replacement and double replacement reactions. Because in any chemical equation or reactions, elements and compounds may react and produce other possible elements and compounds. Again, this is good for single replacement and double replacement reactions. If a compound reacts, it must be broken down into its elements. And then if a compound is formed, it must be put together from its elements. So therefore, if we use the table of values for formation enthalpies and what we know about Hess's laws, we can determine the enthalpy change for any reactions. We will apply this concept in the lab to determine the heat of formation for magnesium oxide.